Hey there, peeps! Our next topic regarding linear momentum is the analysis of elastic collisions. Elastic collisions are defined by two things. One of which is that total linear momentum is conserved, which is something we would expect anyway, so long as there are no external forces. As long as they're all internal between the objects interacting, we're good with the conservation of momentum, and that's going to be true for any situation, so absolutely for inelastic collisions. What is not true, though, is that total kinetic energy is not conserved, okay? So total kinetic energy is not conserved. It would not be true to say that it is. It's not, because in this type of collision, what happens is that energy, kinetic energy, is transformed into other forms that are dissipated into the environment in the form of deformation of materials. So we have heat, we've got the sound and vibrations and all that. What we can say here symbolically is that momentum naught, or momentum original, equals momentum final, but kinetic energy original does not equal kinetic energy final. There's going to be a loss there relative to kinetic energy. That energy, again, goes to the environment. So what we have here is, and actually this particular case is easier to analyze than its counterpart, the elastic collision. That'll be done in other videos in this series. What we will look at then is just the conservation of linear momentum, the linear momentum equation. So here it is. Here's the before part, P naught. So we have m1 v1 naught as the momentum of object 1, m2 v2 naught, the momentum of object 2. Okay, and they combine like this because here's the action in an inelastic collision. What happens is that the two objects collide and stick together and become one. They stick together and they actually move as a single body after the collision. And so what we have here is not V1 final, not V2 final, but just VF final. It's the combined velocity. They're moving together, and what happens is that their masses combine over here in order to conserve momentum. This has to be true. V final times the sum of M1 and M2 equals this original piece over here. So they stick together, kind of like boom, there's an accordion kind of thing, they stick together, and we'll be able to simulate this in the lab on a long lab track with lab carts. And there's this great material, you've probably heard of it, called Velcro. Velcro is very sticky, and it does a really good job at simulating an inelastic collision. The inelastic collision, of course, would not be perfect, nor would an elastic one in the real world, but it is a great simulation for it. And so our study should be pretty good when we analyze inelastic collisions, at least within the margin of error and uncertainty of our measurements. All right, that's the inelastic collision. Other videos will feature the elastic collision, which actually is a little bit more complex, even though that's because we have both these factors to consider. And so that will be done in other videos. So for this one, inelastic, we are done. Out!